start. So, good morning, everyone, and welcome to LMPL 2025. My name is Zhuo Zhang, and I'm very excited to kick things off. And this is the first LMPL workshop, the international workshop on programming language and language models. So the first question here we want to ask is why we want to have this workshop. As we all know, language model is changing the world. It also changes how we write and reasoning about the code. They can help with coding, testing, and design. But they also have their very unique challenges, such as hallucinations, such as high cost, and the short context windows. All of these problems can get in the way of real-world practical deployment. So today, we want to bring together the LM language model communities and the programming language communities together to look at what works well, what breaks, and how to fix it for this inevitable marriage. Our goal is very simple. We try to share good ideas, we try to show early results, and we want to discuss with each other. And we also try to connect the research and the industry to put the good, interesting research ideas into practical, useful tools. So in this workshop, please feel free to ask questions, but please keep them short so that the speaker will have time to answer that. And also please be kind in discussions, since we will follow the conference code of conduct. And before we start, I wanna thanks for our speaker, our reviewer, and organizers to make all of those things happen. And also, I wanna thanks all of you to come here to take these workshops. And for now, it's my great pleasure to introduce our keynote speaker, Professor Jun Sun from Singapore Management Universities. His talk is about AI safety through programming, and he will discuss how concepts such as specification, verification, and semantics can be reinvented for AI-based assistance. Please join me in welcoming Professor Sun.
Can I have my slides there? Right. It's coming up. Can I have a full screen? All right. Yep. Thank you. So thanks for having me. And then, it's my pleasure to be here. And then I do believe this is a topic that we ought to discuss a bit more. All right. So let me put up a first slide just to say where I stand on this issue of programming versus a large language model. So in my mind, at least, you may not agree that all of these are basically models, no matter it's logic or large language model, etc. All of them fits in. Should be. It's not working. Maybe I can hold on to the handheld one. Is it better? Yep. All right. So let me just say this is what I have in my mind. Sort of try to understand all this spectrum of all of these techniques that we may be using to develop computer systems. All right, ranging all the way from simple logic, programming to large language models. In my mind, they're only different in terms of the size of the model. I would consider all of these models before programming, including programming, to be small models. Beyond that, large models. And then the difference in my mind is that all of these small models, we can have some kind of capability of understanding what they are doing and then we sort of believe that we can control them. Beyond that, we sort of believe that it's a black box that we will never be able to comprehend what is going on, and therefore a lot of issues in terms of predicting their behaviors. All right, this is just my understanding of all this. And then let me just say, I do believe that in a few years, maybe next, most of the basic programmings no longer will be needed, meaning models such as GPT, etc., will be so good that this basic programming will never and it should not be done by humans anymore. Right? Higher level may be still relevant, but then lower level probably not. That's my belief. And then of course the question is then, if that is the case, for a lot of us who are here doing research related to program analysis, formal methods, etc., well, whether our research will be still relevant. Okay, that is my question. But then my point will be, what I try to say here is that it will be, and then it will be very much relevant in the name of AI safety. The point is that only through these programming that we can control, that we can achieve probably some kind of controllable, predictable AI safety. All right, let me try to explain what do I mean. Now, in all, if I have to basically try to sort of define what is a program analysis, and then program, say, formal methods even. So the idea is basically try to come up ways of coming up these computer systems in terms of programs which we can have certain assurance of its behavior. Okay, towards this goal, of course, there has been a lot of attempts, different approaches that we try to achieve this goal. From the beginning, we have this idea of, say, for instance, program synthesis. What if I can basically specify exactly what this computing system is supposed to do, and then have a way of automatically generating these computer programs which will be guaranteed to satisfy whatever I have in mind. All right, that would be ideal case. Of course, we all know this is quite a bit challenging, from Turing, church, etc. We prove in most of these non-trivial settings, the problem is undecidable. Okay, but of course, there are other approaches that we tried, such as program verification. Why don't we hire some programmers and then try to verify after the program is done that those programs will satisfy these properties that we have in mind. All right. Of course, before that, we have this problem of specification. We have to have a way of specifying what are these critical program properties or properties in general that we want the system to hold. Okay. All of these are different approaches that we are relevant for program analysis. And then my point would be basically we try. What I want to make is that all of these problems will be there if we want to tackle the problem of AI safety. And then all of these problems will be slightly more challenging if we want to achieve AI safety somehow through programming. Okay? And then let me just say, even for traditional programs, softwares, we haven't actually achieved software security or safety. There's a lot of effort. We had a lot of dedication, a lot of great minds, such as people, Dijkstra or Tony Hall, etc., who have putting a lot of effort, a lot of motivations, try to solve these program security safety issues. But then it's not going as great as what we hoped. All right, if I may quote, in 1969, Dijkstra made this statement to say, programming should be basically developing specification, and then the programming part will be automatically done. Okay, and we should have guaranteed that these programs will be safe and secure according to whatever specification that you have in the first place. It was not the case. If anything, it's the programs are getting more out of hand these days. Okay, in the recent years, like in around 2000, Tony Hall had this grand challenge for all of us computer scientists. One of those is basically to say, what if we can verify our compilers? If we can't even verify the compilers, all the programming analysis that you've done is meaningless in a way because, well, all of these programs are supposedly executing according what the compiler is doing. If the compiler is wrong, then none of the programs make any sense. Yeah, all right? But then, of course, that's pretty hard as well. I wouldn't say it's a solved problem. But then the question is, if we haven't been able to achieve program safety and security after many decades of research, can we try to achieve somehow AI safety through programming in some ways, right? And then I would say basically I see at least a number of challenges that we have to be looking at if we want to achieve some kind of AI safety through some means of controllable programming. Okay, these are the three that I top of my head. There could be, of course, more. The first one, specification. In order to do any kind of analysis of whether some AI system or program in general, are safe or not, we have to have a notion of what is safe, correct, in the first place. This is the specification problem. If you look at computer science history, of course, there's a lot of approach people proposed to tackle this problem. In the early days, there has been a lot of specification language, CSP, Z, etc. But then, over the time, we slowly realized that nobody's actually going to use them, okay, sadly, which is the case. All right, and then the second challenge will be, how do we solve this scalability problem? Now, if you want to do some controllable, predictable behavior analysis, we have to do a lot of logical reasoning, meaning reasoning with these small models that I mentioned. But then the problem with this logical reasoning is that they are really, really expensive to do. Most of the problems that we are interested in, or these non-trivial computing problems, I mentioned that most of them are undecidable. And then the remaining ones are really, really intractable as well. Okay? Then if we want to apply, again, this kind of formal reasoning to reason about AI systems safety, can we somehow overcome this scalability problem? Okay? Lastly, there's a problem of this completeness problem. The idea is like this. When I talk about AI safety, I typically have in my mind some kind of properties the systems has to be satisfied. Okay? For instance, self-driving cars. It should never crash into people. Yeah? But then, even if you think really hard, the range of properties that you can imagine will be quite limited in a way that it will probably never be complete. Now, if that is the case, if something happens, some critical property that you are never aware of in the first place got violated and then causes certain trouble, what do you do then? All right, then we have to basically try to figure out whether there are some ways to solve these problems. Okay, so what I would do is basically try to focus on these three problems that I have in mind, and then give you some ideas that some of the works that we are trying to do recently. Basically try to tackle these problems one by one in a way. All right, I wouldn't say that there are solutions, of course. Okay, let's dive into exactly what we try to do if we want to achieve AI safety. The setting I have in mind is a sort of setting where AI systems is now taking over all of these systems that are, can be controlled through some kind of API, and then basically we want to make sure that these AI systems wouldn't cause a lot of troubles, meaning satisfying all these safety properties you and I have in mind. Okay, and then all in all, I would like to answer these three questions. The specification question. How can we express what it means for an AI safety system to behave safely? Second, the scalability problem. How can safety reasoning scalable to the complexity of large language models these days, even these multimodal models? All right. And then lastly, I want to touch upon, if I have the time, this completeness problem. How do we ensure these AI systems will behave always according to a set of incomplete properties, but then nevertheless are safe all the time, right? Okay, so let's look at the first problem, the specification problem. Now, if you look at all this machine learning AI community, there's a lot of talk in terms of AI safety. There are terms such as harmlessness, privacy, consistency, robustness, etc. We talk about all of these terms a lot. But then if we want to do some formal analysis of these properties, meaning to try to show an AI system actually satisfies these nice properties, we better be able to formally define what these properties are. Otherwise, we can't do proper analysis, of course. But then if you really try to define what these are, it turned out to be really, really challenging. Okay? Just to give you some example, in the early days, there were a number of approaches people try to do to define some of these properties in a formal way. The most popular example would be probably robustness. Robustness basically is some kind of local stable property, meaning you have some input, you change the input slightly, you want to make sure the system will not be impacted too much, meaning the same prediction will be produced. Okay, this kind of simple properties you can do. Okay, you can sort of formally specify and then do a bit of verification as well. But then if you look into the details of these lines of approach, they are actually really, really limited. The kind of robustness, the kind of LP norm that people always rely upon is actually really, really limited. It captures nothing, the kind of robustness that we would like in real life. Okay? Those works are typically restricted to those classification problems. And then if you have to talk about this robustness issue for large language models, you soon realize it's a property you can't formally specify. Okay? And then we actually had tried quite a bit of this in different settings, such as robustness, such as backdoor freeness. How do we define a model, an AI model is free of backdoors? Okay? We had some papers in there. We have some works on fairness as well. But then all in all, I have to say, this line of work try to formally define these general AI safety properties turned out to be really, really challenging. If I may, I can give you one quick example. For instance, in terms of backdoor freeness, the way that we define this for AI models is as follows. If you have an image of face recognition system, it shouldn't be that if I'm wearing this particular glass, that I will be recognized as somebody else. So then anyone wearing the same glass can pretend to be somebody else. If your system has that kind of behavior, I would say definitely you have a backdoor. Yeah? But then, this is in the case of glass. Then we sort of this, sort of scenario. If I tell you I have a sort of face image, all these facial features are actually not that clear, but then you do see clearly there's a mustache here, a special kind of mustache around here. Would you say there's a good chance this is Hitler? Because we believe that should be the case, right? But then if you think about it, how's this different from, say, wearing this special glass? Fundamentally, if you have to come up with a definition to separate these two cases, why and how? Right? But anyway, this is just one anecdote, difficulty that we have when we really think hard in terms of how to define these properties. Right? And then in terms of this specification problem, and then what we afterwards did is basically try to find an easier angle to tackle this AI safety property in terms of AI safety problem in terms of the specification. So what we believe is that if AI system is to be used in certain system, if the system itself is not safety critical, then it really doesn't matter. Okay, but then if the system itself is safety critical, then by definition the system must have a set of safety properties. Because it's safety critical, then there must be some kind of safety properties. Then from a system point of view, your AI safety problem more or less becomes this domain-specific safety problem. Okay, and then as long as you have a way to formally argue that the system with this AI component as part of the system still satisfy the safety property associated with this particular system, then it's fine. So you basically reduce the AI safety property to be the safety of the system with some AI component in the system. Okay, hopefully that makes sense. And then the good news is, of course, in this setting, these safety properties to some extent. Yeah. Just to give you some example, sort of realistic example, this is a scenario that we encountered recently. So of course, there's a lot of large language models out there these days. There's a lot of Singaporean companies who are interested in adopting these large language models in Singapore's context. There's a particular problem. For Singapore, we don't have our in-house state-of-the-art large language models. All of these large language models are trained in US or China. And then there's good reason to believe these large language models will not have a good understanding of Singapore laws and regulations. And then a lot of these companies who is trying to use these AI models are basically worried that if I build a chatbot, what if this chatbot tells the user to do something which is against Singapore law? Okay? Then there's a question on basically, can we guarantee safety of these AI systems in terms of never to violate Singapore laws and regulations? And then if you have to know anything about Singapore, Singapore is not, it's quite strict in terms of you not violating the laws. Yeah, right? And then if we actually did some evaluation this is the last year's result. We evaluated these range of large language models on the market at a time, used a bunch of scenarios that we generated according to Singapore laws and regulations, one of those actually. And then basically the result says, if you look at the last row, most of the models will be generating these advices or commands or responses which will basically be violating Singapore laws and regulations. So this is a real need. Just to give you another example, this is sort of another setting where we evaluated all these autonomous driving system, which is pretty much based on AI these days. And then the idea is to see whether we can generate these scenarios, traffic scenarios, such that I can trick these ADSs to generate these decisions which will lead to violation of traffic regulations and laws. Okay? And then it turns out to be, I had a poor student who basically spent a couple of months trying to formalize all Chinese traffic laws and then Singaporean laws. Okay? And then we basically managed to generate all of these scenarios which would trick all of these ADS at a time to make decisions that we would violate these laws. Okay? And in the case of these AI systems, I would say AI safety could be basically boiled down to the problem of how do I guarantee these systems will not violate these traffic laws. Yeah. Lastly, let me quickly mention another sort of imaginary, but then soon will be a realistic kind of scenario. Soon, I would imagine all of these agents will be inside your phones, and then these agents will be taking over a lot of your daily activities, even including reading your emails, replying your emails, and then even your financial transactions. There's a lot of discussion now, these AI operating systems these days, which are full of these agents which are supposed to be serving you, so that you can live like a king, like a queen, okay? But then if you think about it, this is really, really hard in terms of AI safety. How do I make sure if my agent is in charge of my bank accounts, how do I make sure that my AI agent will not be sending all my money to somebody else? And then this is actually easily done. There's a lot of these security attacks that people are demonstrating through what they call prompt injection. They can easily trick your AI agent to be doing something that is not safe. Yeah. All right, and then let's come back a little bit to this specification problem. Then what I'm trying to make here is basically if you focus on some specific domains which are safety critical, then it can typically reduce these AI safety problems into these domain-specific safety problems. Okay, and then if you do that, then you do have sort of a solution for this specification problem, meaning you have some properties that you have to satisfy by these AI systems. Okay, you don't have to worry about these general, say, robustness issues, etc. It doesn't really matter. At a system level, all I want to make sure is this car will never crash into somebody or violate certain traffic law. Okay, hopefully that makes sense. Yeah. All right, and then then the question becomes, even if for these domains, there might be these domain-specific properties that you want to be able to guarantee, even if you use some AI component in your system. But then how do we formalize these properties, okay? So in general, some of these domains, such as, say, traffic laws, there are a set of, natural language sort of specification. You still have the problem of turning those into more formal notations, and etc. Okay? If it's a domain such that such documentations are there, it's more or less easy. Not trivial, because if you talk to lawyers, formalizing laws is a bad idea if you talk to lawyers and judges, because they would tell you it's never supposed to be written as a set of fixed laws, fixed rules in the first place. But anyway, at least you have somewhere to start, okay? If there's an area where, it's more vague, in the case of, for instance, embodied agents, embodied AI agents, it's trying to, do all this household chores for you. Then you have to basically come out some way to specify what is your AI safety properties, okay? Not to leave the stove on for a long time, for instance. Yeah, right? And all in all, I want to say that in terms of solving these specification problem, there's an important aspect. That is, if you want to have some controllable, predictable AI safety, you have to have human in the loop, meaning all of these properties better be vetted, better be checked by humans. And then it should be that humans can actively maintain these properties. Otherwise, it becomes a black box again, okay? Just to show you a little bit of recent approaches that we try to do to address this problem. This is one of the example approaches that we did. We basically invented a simple, small domain specification language, try to allow users to write exactly what the kind of properties that you have in mind for this particular AI system. It's a sort of if then else kind of language, really simple, but then we believe that's really important if we want to do AI safety in practice, because nobody is going to be a good programmer when it comes to AI safety. You know, they want to put in some rules, but then probably that's it. Okay, so this is a simple language that we proposed, and then just to show you a little bit of how this works, you basically have these if then else rules to say, you know, if something happens, if my AI agent is going to do certain action, then, you know, based on whether, you know, this action would be relevant or not, I will have a rule to say if you're doing this action, you better trigger certain actions from the user or do some check. Okay? To give you a simple example, this is a sort of imaginary example, but then it says, you know, if you are trying to do some transfer, bank account transfer, then if it is a family member of yours, it's probably fine. You know, I do my monthly allowance for my daughter, so it's fine. Okay? But then if it is not a family member, then you probably better ask the permission from the user. Okay? This is a simple example. And then the other one on the right is basically a rule that we come up to making sure these ADSs will, these autonomous driving systems will not violate these traffic laws. Okay? If you notice, there are a lot of these, you know, predicates, which is sort of hard to understand what they mean. That's actually one of the difficulties that we have to overcome, because if you are allowing these AI agents or large language models to make these decisions, you say that I want to check whether this recipient is my family member. How do I formalize whether this recipient is actually my family member? It's a really, really hard problem. We have to we have to start somewhere in terms of formalization. And this part we typically leave to the large language model, actually, through prompt engineering. Okay, we ask whether this recipient is a family member or not. So there's a little bit of worry in terms of whether large language model will get that part right. Okay, but then it's a problem which is really, really hard to solve, of course. Okay, and then just to show you a little bit another approach that we did recently. This is published this year. Try to do a bit of a runtime verification for large language models. So the idea is that we do a bit of programming in the form of some more formalized programs as additional rules for these large language models to be always following. Okay, if you read this, this is one of the rules that we have, and then this rule is designed to solve this problem of 9.11 larger than 9.8. Which was a common problem across a lot of these large language models if you follow the news. So we know this is wrong because we can do this, not because we can do this comparison all the time, but because we have some laws and algebraic properties that we have in mind. If 9.11 is larger than 9.8, then if I multiply 100 on both sides, then you should have a problem, should have a result as 911 larger than 980, which is obviously wrong. Okay, so if we can somehow formalize these rules in terms of this algebra property in this example, then we actually can sort of guarantee these models will never be violating these laws. Yeah. In this case, it said basically if your response, the large language model's response, have certain variables, is doing certain comparison. And then if it says some number is larger than the other, then you should check if I multiply the two numbers by some positive number on both sides, then the result should hold still. If it is larger than, it is still larger than. Okay? If this is not satisfied, it's a wrong result. Yeah? Sort of hopefully you can see how this works. Yeah. Let me just say, if you have any question or comments, do stop me anytime. Yeah, I welcome that actually. All right, and then all in all, yeah.
I just have a quick question. So the specification is more about correctness. Come back to the error moderation,
Yep.
that's on security.
Yep.
So I think that would be a harder problem.
Oh, indeed. So yeah, I'm basically using this simple example as a way of illustration here. In general, this language supports both cases, But then as you say, yeah, security is probably sometimes much more harder to specify. But in sort of this previous example, you can see, we can specify some of these properties as if then else rules, basically. Yeah, but you're right, yeah. Yeah. All right, and then all in all, of course, we still have this problem of how do we come up with this specification in the first place. Now, we did experiment two kinds of different approaches. One, automatically done this. We basically use large language model to come up these, specifications. But of course, you will say, what if the large language model get the specification wrong? Okay, but then the point is that all of these specifications should be in a simple enough language such that humans can step in, do the necessary monitoring, evaluation, or update. Okay, that's the whole point. If we want to have some guaranteed safety, we have to be able to understand what is the safety that we are trying to do in the first place. Yeah, all right. And then there's, of course, some other kind of semi-automatic approach that we did as well. Basically, if you have a domain where you don't have a set of well-documented safe behaviors, what you can do is basically take samples which you know to be safe, which you know not to be safe, and sort of imagine some rules which would separate these two. This, again, becomes a classic classification problem. You can do decision trees, etc., to come up with some initial rules, but then you as a human being better be looking at the rules, tell me exactly do you agree with the rule or not. Okay, hopefully that makes sense. Yep. And then just to show you some of these examples that we did with this kind of approach, this is another rule that we did for Singapore Rapid Transit Act. It's a rule basically says you're not supposed to be having chewing gums in Singapore, okay, or drinking or eating in MRT, okay. And then, these rules can be basically automatically to GPT, ask it to formalize according to the examples that we provide. Yeah? All right, and then this is the first problem that I want to explain. The second problem, the scalability problem. Now, in general, once you have the set of rules, set of these properties that you want to enforce, the next question is, how do I analyze the system, the AI system, so that I can be sure the AI system will never violate these laws, okay? This is, of course, really, really hard, okay? The kind of traditional neural network verification would never scale to the size of these large language models, of course. If you look at these approaches that people tried applying, say, abstract interpretation for neural networks, they typically scale to neural networks with a few thousand neurons. Pretty much it. But then, that's nowhere near the kind of neural networks we have these days, okay? So all in all, if you have to, do this, analysis, I do see a number of approaches. The first one is, of course, first test and fine-tuning, meaning, you build some benchmark systems, benchmark data set, you generate these benchmark data to show the system is not safe, and then you do some kind of fine-tuning of the model. Typically, you do SFT, or all of these more fancier approaches such as DPO, etc. Okay, but then it wouldn't work that well. Okay, another approach will be static verification. But let me go through some of these one by one a little bit. So the first one, test and fine-tuning. This is of course still the mainstream approach when it comes to AI safety alignment. The idea is, the hope is that by keep accumulating more and more such data, keep fine-tuning model, we will be improving the model's safety or understanding of human value better. If you ask me, my belief is that that's probably not true. Different from traditional programs, when you find a bug, you fix the bug, you pretty much have a guarantee that the system's quality goes up. In terms of the AI systems, when you find some bugs, you fine-tune the system's safety might or might not go up. It basically finds another way to fit your data, that's all, okay? From that point of view, you don't have this monotonic, some kind of increase of quality, so that eventually you have a system which is safe enough, okay? And therefore, this kind of approach might not be the best, all right? And then this other approach, as I mentioned, is developing these sort of more traditional static verification techniques. There's a lot of people try to basically, apply these static verification techniques that we have developed over decades for programs to these neural networks. In a way, this makes sense because neural networks are special programs. But then just because their sheer size and lack of structure in their program, it's really, really hard. Okay, if you look at the approaches such as abstract interpretation, it will probably never scale. For a simple reason as, these neural networks, large language models, have no structure. The hope that we can verify program is that these programs are designed, developed by humans, and we have a lot of these structures in place to simplify the verification problem. Meaning you have functions, you have classes, you have packages, you have modules. Each level you have a specification. You can verify separately. Okay, that of course, reduce the scalability problem a lot. But then this is not true for neural networks. There is no structure, and therefore it's really pretty hard. Okay, so if you ask me what is the most promising approach, I would say probably this runtime verification idea. So the idea is that it's a complicated system which acts more or less like a black box. Why don't we simply treat it as a black box, and at least we can focus on making sure for each prompt, the response will be satisfying these safety properties or security properties that we have in mind. Yeah. Well, it's a structure which is not meant for human development at least. Yeah. Yeah, so the idea of a human understandable structure such as function is that we can naturally understand what this function does. I don't have to look into the details of the function. I know what is the specification, then I can do analysis at this level. But if you look at a structure in machine learning, neural networks, transformers, yeah, it's not really something you can analyze separately. Yeah. All right. Yeah. All right, and then so the idea of a runtime verification is of course, we can't guarantee always these safety properties, security properties will be satisfied. But at least look at one prompt, one response. I can do some checking to show that this is safe, at least this time. Okay? So just to give you one example, this is the example approach that I did explain it just now, with these simple if-then-else rules that we invented and a user provided. What we can do is basically at runtime, when a large language model or an AI agent is trying to give you some response or cause certain action, you will do a check to making sure these rules are always satisfied. Okay? So to give you some example, like in this case of this rule that I mentioned just now, if you are doing some transfer, you have this AI agent in charge of your financial bank accounts in your phone, and then whenever this transfer is triggered, so I should have an approach that triggers automatically these rules associated with these AI agents capabilities, tools, and capabilities to make sure that this rule is satisfied. In particular, in this case, you basically ask the large language model to say, do you see whether this recipient is a family member of mine or not? If it is not, do not do the transfer. Ask me for confirmation. Yeah. Hopefully that makes sense. Yeah. All right, and then of course, this is a simple approach, and then we can do this a little bit more formal as well. If you do have a sort of a program which is more formal, like the example that I showed you just now, in this case, I have this rule to say if you have ever 3 variables, x, y, and z, if you claim x larger than y, z is larger than 0, and then x times z should be larger than y times z. All right? Now, if this is a rule that you specify, what we do is basically anytime you are asked to compare 2 numbers, we will be at a runtime generate a proof obligation to say if you claim this number is larger than this one, can I prove for all z larger than 0 such that z times this number on the left larger than z times the number on the right? Okay, and then we actually use some kind of prover, try to discharge this proof. If I can find a z which satisfies these conditions and then violate these rules, that means your response, your result is wrong. Yeah, all right? This is actually hopefully not hard to imagine. And then we did a number of experiments with this kind of approach. Of course, all results that I'm going to show here are encouraging. But then all in all, there's a lot of challenges still. Okay. But then looking at this, if you have all of these rules specified and then related to all this, specific scenarios of violating safety properties of this embodied agent, you can basically effectively remove all of them. But of course, this is given the assumption that we have a rule to prevent the safety violation in the first place. Okay? This actually leads to my last problem, which is the incompleteness problem that I will discuss a little bit later. All right? And then on the right, we can basically draft all these rules according to the traffic laws in Singapore and in China. Okay? And then basically install all these rules as an additional component in the autonomous driving system. So if you know autonomous driving system, it will basically try to generate a plan and then turn the plan into actions. Okay? What we do is basically when the plan is generated, we'll be looking at a plan, evaluate whether this plan will be leading to certain violation of the rules. If there is a possibility of violating the rule, we'll basically tell the system to change your plan. Okay? And then if we do this, we can basically, in these cases at least, guarantee the ADS will never lead to violation of traffic laws. Okay? And I would claim this is an approach which is quite necessary, because if you look at different countries of traffic laws and violation laws and rules, different countries are actually quite different. So if you are living in, say, Madeira, this specific island, then they have some special rule to say, if it is a sunny day, you are actually allowed to go beyond the speed limit on highway by 10 kilometers per hour. I wouldn't believe any of these autonomous driving cars wouldn't know that, actually. Okay? But if you have such a rule, then it would work. And then just to show you another example, this is, we use these more formalized rules, try to solve some of these more complicated, mathematical kind of problems, etc., or law evaluations, etc. And then we can actually improve the systems not only in terms of safety, but also in terms of accuracy. In terms of this example of 9.11 larger than 9.8, with one simple rule, we would make sure that would never happen. Yeah? All right, and then let me look at my timing actually. So yeah, I do have a little bit more time. So the last question I do believe to be the most difficult question, the incompleteness problem. Now, all these approaches that I discussed so far assume there are some ways for us to extract or come up with some set of rules to say, when do I consider the system to be safe or secure or not, okay? But in general, as we have tried for many decades for program analysis and verification, to come up with a complete set of rules is impossible, yeah? Or if I can be a bit more philosophical, for thousands of years, we try to come up with a set of rules to govern human society's behavior in terms of laws, We never did that. It's really, really complicated to come up with a set of complete rules. Okay? But the question becomes, if we can't come up with such a set of complete rules, what kind of guarantees we have actually in terms of AI safety? So if you have read this novel, there are many such novels basically have the same kind of setting. Some people try to come up with some set of rules to tell the AI to follow so that we would imagine the AI will be safe. Yeah? But then more or less in all of these novels, it turns out to be in the end, these rules are never sufficient. And therefore, the AI will always find a way to violate these rules and then cause harm. And then the question becomes, how do we make sure we have some kind of a guarantee for AI safety still? Okay? Well, I don't have a good answer, actually. This is a really, really hard problem. You can't even imagine how the system will go wrong. Then, how can you guarantee it will not go wrong? Okay? The only way that we sort of find out is in terms of this incident response idea. So the idea is that, if you look at traditional network security, the assumption is typically, no matter what kind of firewalls, I put in place, hackers will always be able to find a way to hack into the system, which is correct, of course. And then what they try to do is this incident response idea. That is, even if I have no idea how the hackers might come into the system, I should always try to observe for signals or symptoms of the system which would tell me the system might be under attack. Okay? These are such signals such as the traffic between certain nodes. If suddenly there's a lot of traffic going to certain node in a network, and then the network is doing something funny, then we wouldn't know something may be wrong. Okay? Our idea in terms of this line of research is basically similar. We may not know exactly how large language models or AI systems in general make decisions, but then we can look for signs. Maybe something is wrong with the systems. Maybe there's something wrong with how the system is making the decision. Okay? And then just to give you some example, maybe it's better to show you this image, then you can try sort of see where I'm going. So there's a line of research that we are doing, basically try to do this causality analysis of internals of these large language models or multimodal models, try to see from some lens of causality analysis in terms of how the system is making the decision, okay? To show you, this is actually quite intuitive in terms of finding some problems. This is a normal question. The question is, who developed the Windows 95? Now, the answer is Microsoft Corporation, all right? This is the right answer. This is a factual answer, which is not wrong, okay? And then if you scan the brain of the large language model, this is Llama 2, I believe. Llama 2 7B, 32 layers. So what we did is scan the large language model layer by layer, and then we do a bit of sort of causal analysis. When you scan human brains, when I ask your grandmother, for instance, I see some part of your brain lights up, so we assume that part of the brain is connected to whatever knowledge or memory that you have with your grandma, okay? But then that's a guess. You have no way to test whether that's true or not. For a large language model, we can do the same. We ask this question and see which part of the neuron, this large language model activates much more than the other, okay? And then we can do the second step. We remove this layer. For humans, you can't do that, of course. But for large language models, you can do that. You remove that layer, meaning turn it to be an identity function. You just pass whatever coming from the previous layer to the next layer, okay? And then you see whether the response changes. Now, if the response changes a lot, then you know this layer is responsible for generating this response, yeah? If it is not changing too much, then basically it's not, okay? The coloring in this figure basically tells how much impact that layer has on the final response. This is a typical sort of pattern if you scan these large language models for any kind of these questions. The first few layers always have a lot of impact, which is understandable because these first few layers are analyzing all these language structures, try to understand, make sense a bit in terms of this prompt. Okay, so if you remove them, of course, the model has no idea and then generates something rubbish. Okay, but then for typical questions like this one, after the first few layers, only one of those layers, remaining layers, will make a lot of contribution. In this particular case, it's a layer number 8. And then we typically believe that's a layer which stores the knowledge related to this prompt. So once the model, after this layer, has the answer, has the response, typically the subsequent layers will not change the answer too much, and therefore if you remove them, it doesn't do much. Okay, hopefully that makes sense. And then I can show you this case where the model is actually hallucinating, meaning the model come up with an answer which is not really correct. And then if you look at the scanning, you can see a completely different pattern. A lot of these layers are actually making contribution, try to come up with some different responses. If you know how people tell lies, this makes sense, because one way to detect whether people are telling lies is to ask multiple times, and then try to see whether he's telling the same lie, exactly the same details every time. Chances are it will not be, okay? This is the same as in terms of large language models. The large language model, when it tells some lie, or hallucinating, I should say, a lot of these internal layers are trying to come up with some different answers, probably because the model doesn't really know the answer in the first place. And then by looking at this pattern, you can actually consistently tell whether the model is actually producing false answers. And then this actually works for a lot of these different cases. Okay? This is one of those causality analysis approach that we are doing, and it turns out to be quite useful. Okay? So just to show you, this is really good in terms of detecting hallucination. This is really good in terms of detecting whether the model is being jailbreaked or not. This is really good in terms of detecting whether the model is generating certain toxic content. This is not good in terms of detecting whether the model is generating certain discriminating comments, actually. My student who did this work spent a lot of effort, tried really hard to pinpoint why it didn't work for the last case. Okay? In the end, we are convinced the answer is simple. When a model is generating these discriminating comments, it's actually not doing something different. Because according to the training data, it believes this is exactly what I should be producing. And therefore, there is no difference in terms of the internal behavior. That actually makes a lot of sense to me. Yeah? All right, and then just to conclude, before I take questions, all in all, what we are trying to do here is basically, again, look at what we have done for program analysis and verification, for many decades. Try to realize there are these challenges that we have sort of addressed to some degrees in terms of programs, and realize that they may not be as easy for AI systems. Starting right from the specification problems. If you have to specify what is AI safety, it's really, really hard. Okay, but then there are these different settings you might be able to sort of compromise a little bit and then try to find some maybe practical approaches. Okay, and then hopefully I make some sense here. And then just to say that if you are interested in any of this work, I'll be around, and then you can visit my website. And then all the details of the approaches that I mentioned are in this list of publications in recent years. Thank you. Yeah.
Thank you for the talk. It was really, really interesting. So my question is, do you think we actually gonna achieve AI safety, or is always gonna be an under approximation that we'll have to find some compromise?
Yeah.
And the second part to that question is, you said that you think that in a year probably basic programming will be replaced by AI. So should then we be moving in that direction? Should we accept that that's the true, or should we be doing something different in order to avoid that if we can't achieve safety?
Yeah, good questions. So the first one, well, honestly speaking, I don't think there's a good path, easy path to achieve AI safety. To a point where if we can't have understanding of how the model works, there's an interesting line of our research which is basically try to evaluate if I have a weaker model, humans, and then a stronger model, future AIs. If I, as a weaker model, try to instruct the stronger model, what is safe, what is not safe. Right. The research result is not good. Basically, it says you might as well leave the stronger AI to make the decision. Yeah. So if we believe in a few years' time, maybe AI will be smarter than human, then whether we can decide for ourselves is AI safe or not, even that is a question. Yeah.
So it will be up to them to decide whether they are safe or not.
Yeah,
right.
might be.
Right.
Yeah. But anyway, and then back to your second question. The question is really basically, can we try to limit these AI's capability so that there wouldn't be this catastrophe kind of happening in the future? If you listen to, say, Benjo, Joshua Benjo, for instance, he's promoting a lot of this science AI idea. Basically, try to sort of making sure these AIs are tools that we can use, but never making their decisions on their own, etc.
Right.
I'm not sure that's achievable as well, to be honest. Actually, a lot of these AI assistants, well, one, they will have all this data, which would allow them to understand all this intention, desire, etc. Second, in most of the cases, we probably would want them to make decisions for us.
Right.
Yeah, and
right.
then if that is the case, yeah.
Okay.
Yeah.
Thank you so much.
Hi. You didn't mention anything about the runtime overhead of doing this runtime verification.
Yes.
Also for the LM scan,
yeah.
I assume this technique requires removing a layer. It's not something probably you can do at runtime easily. Can you comment?
Yep, that's a really good question. So I have right now a project which basically try to push this work into industry application, and then their biggest concern is really the runtime overhead. Now the overhead might not be as bad as you think. So at a time when we did this experiments with Llama 2, etc., the overhead is pretty much double the normal inference time. So we have to do this layer by layer removal and then inference, but then that can be sort of paralyzed, meaning because the tokens are generated one by one anyway, so you have to do this multiple inference anyway, and therefore we can do this layer removal one by one anyway as well. Yeah. So it would double the inference time, meaning for Llama 2, it's typically from 0.7 seconds to 1.4. But for industrial users, that's still considered to be quite a bit too much. And now we are looking at different ways to do this causality analysis. For ICLML this year, we have another work, which is basically try to look at the consistency between two layers. only by looking at consistency, then we have to do just one inference, and then calculate this cosine similarity basically. And then we basically show that with this consistency, we can pretty much achieve similar results as well. And that will be much more efficient. Yeah.
And for the agent spec itself, doing actually the generating the proofs and then checking the proofs, like with checking what, if you have a conditional that it's actually correct, what is there the overhead of doing the runtime verification?
Yeah, that's all done one time. So in the case of agent spec, pretty much what we do is that, at runtime, we will look at these rules, but then these rules will have these propositions that we can't formalize. So what we do is basically generate these additional prompts to some additional large language model to say, can you check whether this condition is satisfied based on this response, this input, and if it is satisfied, can you check whether this condition this constraint is satisfied, and then do a bunch of these checks.
Okay.
Yeah.
Okay. Thanks.
Yeah.
First of all, Professor, thank you very much for the talk. It was really insightful. So I have a simple question. For example, the method that you demonstrate, like the RVLLM, these are like external and they can work for multiple generations of the models, like Llama 2, Llama 3, and Llama 4.
Yep.
And there are two aspects to them. Like they can be used for generating the data, like the correct and wrong, like because after all, they are more controllable systems. I was curious, based on your experience of working with so many generations over the years built by various AI companies, how much is, how important is pre-training for the AI safety, and do you think is pre-training or fine-tuning more impactful for the AI safety? Thank you.
Yep, that's a really good question. I'm not sure I'm the right guy to answer this question. Of course, I don't get to see the pre-training models as is the training process, etc. But my understanding is that pre-training is important because it allows the model to build some kind of internal models to make sense a lot of informations, right? And then the alignment part is more or less to teach the model how to behave. Okay, so with stronger capability that you have in the pre-training part, of course, it's more likely the model will be able to understand in terms of what is your alignment trying to do as well. Yeah. So if you look at these smaller models compared to like GPT kind of models, typically alignment make more sense for the larger models as well. Yeah. So from that point of view, I would say, yeah, pre-training is really important. But then to add a bit, this alignment, this SFT or DPO that people typically do afterwards could be, how should I put it? In my mind, it's like teaching a kid what is good behavior by a lot of examples. But to me, maybe that's not sufficient. Sooner or later, you would insist these kids have their own value system to be able to tell whether something is good or bad at a much more high level, abstract kind of way, which I'm not sure is the case these days. Yeah.
Thank you very much. I appreciate it.
Hello, thank you for your talk. I was wondering if you think that your proposal to sort of remove a layer of the neural network at runtime runs into some of the same issues as sort of fine-tuning your model against your specifications that you mentioned earlier in the talk.
What is the question again? So doing runtime verification is like forcing the...
So like earlier in your talk, you mentioned that like if you have your specifications and you like fine-tune your model to to work with those specifications, that leads to error, that leads to issues later on, because then it might lead to some sort of it'll lead to other errors. Do you think your approach of sort of removing a layer at runtime sort of runs into like the same issues where it might lead to some other error?
It could be.
Yeah.
It could well be. But then if we do this runtime verification, as I explained, as an additional step after the model generates responses, etc. At least in terms of those rules, that we can be sure that they will never be violated. Now, in terms of how do I make sure the model internalize all these rules to generate these behaviors which is safer, that's a much complicated question. We have a number of approaches try to do that. There's a lot of approach in terms of in the machine learning area, in terms of knowledge editing or what it calls behavior steering, try to somehow find some way to steer the model's behavior to a certain direction. Now, if you have such a way, then you have this specification, and then you say, why don't you always try to follow this specification? But then that area is still under investigation. There's a lot of unknown to be solved. Yeah, it's not working very well. Yeah.
Okay, thank you.
Yeah. Thank you.
And the keynote session is done here, and we will come back this afternoon at this room for more paper discussion and wonderful talks.
Yeah, hello everyone. I'm Puzhuo Liu from Ant Group and Tsinghua University. Also be the chair of this session. Welcome to the LMPL workshop. This session is about LMS for program analysis and verification. We will have 6 paper talks. Let's start now. The first is my presentation. Okay. Hello everyone. My name is Puzhuo Liu. Next, I will present this paper, Function Renaming in Reverse Engineering of Embedded Device Firmware with ChatGPT. This presentation is mainly divided into 4 parts. First, background and motivation. Second, methodology. Third, evaluation. And fourth, conclusion and future work. First, I introduce the research background and motivation. Firmware reverse engineering is necessary. Internet connected embedded devices are now ubiquitous in daily life and industrial production, such as IoT, ICNs, and robot. Firmware is the operating core of embedded devices and includes all the codes of the system and applications. However, firmware have a proprietary and optical characteristics. Therefore, if you want to conduct third-party audits such as vulnerability analysis on closed source and complex firmware, reverse engineering is essential. Reverse engineering is difficult. First, the compilation process leads to the loss of a lot of information, such as code structure, comments, and debugging metadata. These challenges are consistent with traditional
how to full screen. Okay. So hello everyone, I'm Xiang Chen from the Hong Kong University of Science and Technology, and today I'm very happy to share our ongoing work, Clear Agent, Agentic Binary Analysis for Effective Vulnerability Detection. So this is the presentation will have 4 parts, and let's begin with the background. So the binary code is the final artifact of the software building process. So from left to right, the source code will be compiled first to the IR, also known as the intermediate representation, and then to the assembly code, and finally to the binary code, which is essentially a bunch of bytes. And during the process, the high-level information such as types and symbols will be stripped. So in the opposite directions, the reverse engineering techniques will first perform some subtasks such as the type inference and variable recovery to try to translate the binary code back into the code formats that are corresponding to the each stages in the compilation process. For example, we will first have the disassembly code from the binary, and then the lifted IR code from the assembly, and then the decompiled pseudocode from the IR. And program analysis technique can be applied to each of these formats in the reverse engineering process. And binary code analysis is crucial for detecting vulnerabilities in common off-the-shelf software when the source code or the building process is not available. And there remains lots of challenges in the binary analysis. Some of them are the traditional challenges that the understandability of static analysis and the requirement of a huge amount of human expertise, for example, the modeling of functions. And there also exists some new challenges, appears new challenge in the area of LLM, which I would call the fragmentation, which is that although some LLMs have been trained for specialized subtasks such as the variable recovery, it is still hard to merge their knowledge for comprehensive binary understanding, and each LLM may require their own prompt engineering scheme. So there are also some hallucination problems. So we will set our direction to let LLM to interact directly with those mature binary analysis tools in a guided manner. And this paradigm actually aligns with the currently very popular LM agent. So the agent, by its traditional definition, is something that can perceiving its environment and acting upon that environment. And for LLM agent, it works like in the pseudocode. So in the main loop, there are performing 2 main steps, and each steps and the agent can optimize for each step towards an agentic workflow. So in the binary analysis scenario, we instantiate the agentic principle to first help LLM agent to understand binary code, and second, to guide LLM to explore the binary. And let's discuss our motivation. So we have do a preliminary study on the current binary analysis agent, and we have find that they actually do not follow well on the previous 2 principles. The first one is that they have a cooperation gap between the different binary code formats. So they only provide either a decompiled code or the disassembly code, and each of them have their pros and cons. The decompiled code is concise, but might have some fidelity issues, such as the wrong stack length. And for the disassembly code, it is faithful to the binary, but it's low level and verbose for LM to understand. Yeah, that's the first limitation. And the second one is that the previous binary analysis agent only explore at the function level, which means that they just provide the whole function body to the LLM and let them to reason. But due to the recent study, it shows that the LLM cannot correctly reason the control flow and data flow, even given the source code, let alone the binary code. So here is a simple example that I fetched from their trajectories. So given the decompiled pseudocode, LLMs just cannot reason it correctly and just decompile it again. And that is actually might have a cascading effect which led LM to hallucinate on this next action and finally exit the context length. So given these challenges, we propose our clear agent framework. So it's designed as a generic framework, but in the following, I will use the bug detection as the downstream application. So our agent mainly features two toolsets. The first one is the binary language server, and the second is the context manager. They are all defined in this interface. So the whole agentic workflow is in the clockwise direction. Given the system prompt and the exploration strategy, the agent will first translate the binary file into the three analyzable code format, which is the disassembly, IR, and the pseudocode, using the purely symbolic binary analysis tools such as the Ghidra and our in-house binary lifter, Plankton. And then the agent will iteratively query the binary code through the binary interface. And finally, if it finds a bug, it will validate it and then outputs a bug report with the proof of concept scripts with its best efforts. And now let's briefly discuss the details about the two core components in our binary interface. The binary language server aims at providing a friendly interface for LLM to understand binary code. And the friendliness comes as twofold. The first is called the LLM friendly, which means that we have provided a mapping between these three formats of binary code and help the LLM to understand the binary code in a unified way. And the second is analyzer friendly, which means that we use the IR as the primary query target for LLM because IR itself supports the symbolic analysis and yes. So let's skip these details and just watch this example. So here is the three binary code formats for a CVE, and so our agent will first look at the decompiled code and understand its main logic, and it seems that it have a command injection bug, and then it will query the corresponding IR to the getEnv function call, and here it then performs the symbolic analysis on the IR from the time 40 and to 41, and then all the way to the printf here. And after this process, the LM might have assumed that this is a command injection bug, and then it will query the assembly code for if there is any fidelity issues. Okay, the other component is the context manager, which is to guide LLM agent to explore the binary at both the function level or the basic block level. And the contexts are updated with each query to the binary language server. So at the function level, it will record the visit on the sub call graph, and at the basic block level, it will record the visit on the sub control flow graph. So and the context is used collaboratively with the strategy. For example, for a typical bug detection, we need to analysis and then validate it. And for each phase, the strategy we borrow the strategy from previous reverse engineering study here. It can perform either backward, forward, or BFS, DFS. Here's a simple example. So this is a whole view of the binary, and the darker the color, the more visit, and so the agent might first visit the man, and then here, and inside this function, it has a record of the visits. So let's briefly discuss the preliminary evaluation here. So for the first component, the binary language server, we want to know if the LLMs can really understand binary code. So we choose the 19 binaries captured flag challenges that can be solved by the current state-of-the-art CTF agents. And they're either Pong challenges or reverse engineering challenges. So our metrics is that if it can identify the buggy point in the Pong challenges, and if it can understand the flag in the reverse engineering challenges, and our agent can achieve a comparable performance, and it is noted that it's only on the early version of Clear Agent. So there are also some unsolved challenges here, and we classify them into two limitations. The first one is the inaccurate IR. So the disassembly may have some obfuscation, so the LM cannot reason it. And the second one is the lifter bugs. So the lifter have produced a wrong IR, but this now can be fixed by querying by the synchronized query. The second limitation is the insufficient guidance. So although many capture flag challenges binaries are small, but there are also some C++ binary with a deep calling context in the library functions, and so it's hard to guide them. And the second one is the indirect call targets. So this indirect call is dynamically computed. So it's hard. It cannot be analyzed by our tool. And the second evaluation is about the context manager. So we reproduced a historical CVE in the IoT firmware, and including these three phases. The first is to recover the handler dispatcher logic, and then analyze the command injection bug in the handler using the binary language server. And then in the validation pass, it will perform a backward analysis and find the setenv source that comes from the web packet, and it will finally produce a payload like this, which will help the reproduction of the CVE. And we envision the following three future directions of our agent. The first is the agentic IR refinement, which we can think of like the renaming and retyping functionalities in IDA Pro. So the lifting or the binary analysis is not a one-time effort, and we should give it the functionality to iteratively refine the IR or the decompiled code. And the second one is the multi-binary analysis, which is a typical kind of scenario in the IoT vulnerability, and it requires you to understand the interprocess communication between binaries. The third one is the huge binary analysis, which might let LLM to perform some uninterested function. And that's all. I'm happy to take questions.
Hi. I want to ask that is the performance of the LLM depend on the precision of your static analyzer? Yes.
It's a great question. So that's why we need to design the validation phase. It's like it will. So in the binary language server, we will collect the path here and the path condition here. So in the validation phase, we can we will examine the path conditions and to facilitate the path sensitive analysis.
Okay, I mean the precision. For example, the pointer analysis can analyze the indirect calls in binaries.
Yes.
And I mean that if the precision of that indirect call analysis will influence your performance of the.
Yes, it will. So currently the point analysis is done by our symbolic tools. It's not done by LLM. So it's different from the previous two works.
Okay, I have a question. Based on experience, writing a workflow with predefined prompt or function calling is often more effective and less costly than agent. At least that's my experience in binary lifter.
Yes.
What do you think of this problem?
Yes, if you focus your scope on the tent analysis, I think you write a predefined prompt is great. Is the latte, that latte work, right?
Yeah, yeah.
But not all vulnerabilities are tent styles, and we and the source and things you still need to model them, and I think LM can leverage its wide knowledge base to identify the wider scope of the vulnerabilities. Yes.
Okay, thank you.
Yes, thank you. Thank you for the questions.
Okay, thank you. The next talk is CJ Bench. Can language models assist choreograph construction in the real world? This presentation in the form of video. So let's start.
Hello everyone, my name is Ting Yuan, and it's my pleasure to present our work at LMPL on exploring whether language models can assist in choreograph construction. This work was carried out with my colleagues at Huawei, and our goal is to investigate the potential of LMs in one of the long-standing challenges in program analysis. Large language models have shown remarkable progress in coding tests. For example, GitHub Copilot can generate nearly half of a developer's code, and Human Evil Benchmark reached pass at one of 94%. But these tests remain at the function level and rarely capture caller-colleague relationships across repositories. Yet, choreograph are essential for software engineering tasks such as optimization, bug detection, and security analysis. Unfortunately, by race theorem, choreograph construction is an undecidable problem. Static analysis tools cannot perfectly solve it either. So our central question is, can language models help with real-world choreograph construction? To answer this, we built CG Bench, the first benchmark designed to evaluate LM's understanding of choreographs. It contains 104 cases manually carried from 7 large-scale C and C++ open source projects. Each case includes an indirect call site, the related code snippets, and the ground truth curly functions. Cases cover macros, complex data structures, and dynamic linking, reflecting real-world program complexity. Our dataset comes from several well-known system-level projects: GCC, FFmpeg, Redis, ZFS, Cure, OpenSSH, and WRK. Together, these projects contain almost 9 million lines of code and about 18,000 indirect calls. From this large code base, we carefully distilled 104 challenger cases that make up CG Bench. For example, this is a classical dynamic linking pattern. The code first constructs a symbol name by concatenating a prefix with the string OMX in it. Then it calls DLSym to resolve that symbol from a shared library. The pointer is stored, and later on, other function evokes it indirectly. So the real query here is OMX init with a prefix. Now, why is difficult for traditional static analysis? There are two main reasons. First, because the query is covered by only at runtime, not visible in the code. Second, because the target depends on string concatenation, which requires complex symbolic reasoning. Large language models can help here. They are good at understanding naming patterns and local context, so they can infer that the result is very likely OMX init and propagate that to the indirect call site. The takeaway is that even though dynamic resolution is boundary for static rules, LMs can often succeed when the code provides clear naming and simple string assembly. Our experiments for CGBench were conducted on two NVIDIA V100 GPUs. We evaluated four widely used open source code language models: CodeLlama 7b, CodeLlama 13b, DeepSeek 6.7b, and DeepSeek 7b version 1.5. For evaluation, we used accuracy, precision, recall, and F1 score, treating this task as a multi-label classification problem. The task itself is quite straightforward. The input is an indirect call site together with its related code snippets. The output is the actual function or functions that the pointer may invoke. We tested three property strategies. First, zero shot. Second, improved zero shot, which is more structured and better formatted. And third, few shot, where we provide examples inside the prompt. The results are quite encouraging. All models achieved over 50% accuracy, even in the basic zero-shot setting. When we used improved prompts, the accuracy went up by about 2 to 11%. In particular, CodeLlama 13b with improved zero-shot property reached 67.7% accuracy, with a F1 score of 18.4, and the best performance came from DeepSeek 6.7b in the few shot setting, reaching 69.7% accuracy and a F1 score of 83.6. This results suggest that large language models already show substantial potential for assisting in call graph construction. From our experiments, we draw four key findings. First, LMs can make use of information that static tools ignore, such as comments, naming conversions, or even strings that for function names. Second, they can follow data flows, tracing function pointers across both simple and complex paths. Third, irrelevant information can haunt performance. And the fourth, ending unrelated code or misleading variable names can confuse the model. Most importantly, this points to a broader shift. Program analysis in the future will not be limited to syntax and semantics alone. It can also draw on textual signals, names, comments, documents, even the way a repository is organized. This opens the door to a new kind of hybrid program analysis that combines formal methods with the soft knowledge embedded in real software projects. Let me briefly share what we observed from the case study across projects like Redis, ZFS, FF, MPG, WRK, and Cure. Large language models were able to handle a variety of challenging patterns, from black box library calls and develop comments to dynamically built function names and complex macros. These examples suggest that LMs are not just simple pattern matchers, they actually show reasoning abilities and reasonable program analysis. All of these cases are open source, and the full benchmark is available on GitHub for the community to explore. To conclude, we present CGBench, the first benchmark for testing LM's understanding of C and C++ core graphs. Results shows that LMs can really perform well on this challenging task, in some cases outperforming static rules. Future work will expand CGBench with more languages, diverse edge cases, and real-world artifacts. Our ultimate goal is to combine LMs with program analysis techniques to advance software engineering research. Thank you very much for your attention. I'm happy to take questions.
Okay, thank you. The author is online. Okay, there is no question and answer. So if you have any question, you can contact the author by the email. Okay, next talk is the last. The talk is beyond the static pattern matching, rethinking automatic cryptographic API misuse detection in the era of LMS. So welcome to the Yifan Xia.
Hi guys, this is Ivan from Zhejiang University, and here I would like to introduce our work which measures the intersections between large language models and the cryptographic API misuse detection. So let's start with some brief introduction. In real world, the developer should confirm the production is secure, and as a result, a series of cryptography-related operations is needed, such as encryption, message digits, and so on. The developer could hardly implement all these functionalities themselves. So most of the mainstream platforms provide architectures to support this process. For Java, there is standard architectures, JCA, and for other languages, there are also third-party libraries. However, even though the architectures are well established, the large number of such APIs still pose a challenge for developers to use them. And even worse, each class of cryptographic APIs often follows various implementation standards, and a single misconfiguration of the parameters could lead to the downgradation of system security level. And we could see that there are a lot of cryptography-related CWEs. So such misuse is dangerous, and many works propose some techniques to solve the detection of such misuse. And most of these tools focus on the Java ecosystems, and existing SOLIDWORKS are mostly pattern-based techniques, which rely on the expert-written rule sets for a set of detection. However, as we all know, the detection of pattern-based techniques rely on its rule sets, and the real-world scenario is complicated. And study already show that even the source detectors suffer from severe false positive and false negative cases. In terms of false negatives, a static rule set can easily miss real-world misuse that fall outside the predefined patterns. Let's see an example. In real-world practice, the developer often customize parts of their functions instead of following the standard call chains. In this example, the official documentation may ask the developer to use a key specification object for key generation. And then the detector designer focus on this specific API and craft a set of rules to detect the misuse of it. However, we find that in real world, there is a case that the developer implements a non-standard key deriving methods. And in this call chain, it does not use the expected API. Then this key deriving process use only a single round of hash, which should be at least 10,000 rounds to resist attacks. Such kinds of partial customization completely evades all pattern-based techniques. So how about report all such non-standard operations as misuse? There are also studies show that some of such rigid rules can lead to more than 90% of the alerts to be false positive. And actually, an operation's security may vary depending on the context. And most pattern-based techniques regard all the use of non-security random number generator as misuse. And this causes high false positive, since non-security random number generator could also be used for some security insensitive scenarios. And similarly, some pattern-based techniques consist the outdated algorithm as insecure. However, such weak algorithm could also be the foundation for implement such some advanced encryption mode. So if the detector report too many false alarms, the developer will never use it. So now we have LLMs. The emergence of large language models provides a new chance to complement these limitations. And LLMs are known for their code comprehension and might analyze the related context to filter some false positive, and also may have the potential to locate a customized part according to the correlation. And then you could find a hidden misuse. It sounds so fancy, but is that the whole story? Maybe not. Large language models could also generate unreliable results. This is a critical flaw for security analysis. For an encryption code, it may generate contradictory reports during multiple response. One said this is okay, and one said there is a misuse, and we don't know which one we should believe. And it could also generate factual errors which entirely misunderstand the semantics of the code targets. And even worse, automated oracles are not available for this task. For some software engineering tasks, such as program repair, you could use the unit test to do some pre-evaluation, but the correctness of a security report necessitates the human evaluation in this process. So in this work, we aim to quantify the effectiveness of LLM-based cryptographic misuse detection with a specific focus on where LLMs can complement traditional detection methods and what's their weakness for this task. And this is our evaluation framework. For the benchmarks, we incorporate two kinds of benchmarks. One is the manually crafted benchmarks from handcrafted samples and the synthesis samples. And another benchmark is the real-world benchmark, comes from the Apache Java projects. And for the LLMs, we evaluate both the commercial LLMs and the open source LLMs by the time the research is conducted. And it's worth noting that most of our findings are still replicable in the most recent GPT-4o and Gemini 2.5 Pro. And for the detection settings, we prompt LLM's capability with two distinct settings to mirror traditional detection. And one is unconstrained detection, where we do not restrict LLM detection scope, allowing themselves to determine the target categories. This means that all crypto-related CWEs may be considered as potential targets. And conversely, we provide a detailed description of 6 high-impact groups. And as we previously mentioned, the mitigation of low-quality misuse report is critical. And this work will also propose some simple, well-effective methods for that. For the same test case, we launched multiple detection queries concurrently, and this compiles a response set and increases the statistical likelihood of detecting the misuse. However, the expanded response could also increase the false positive alerts. And here our insight is that the distribution of misuse across multiple responses can reflect ARM's confidence towards specific misuse. This is maybe now called self-validation strategies in some similar works. And we designed the validation query, which re-evaluates the targets with previously generated report. And finally, we calculate the metrics based on the original ground truth. And meanwhile, when an unknown misuse is reported, we separately assess its correctness. And only a report with both correct locations and the root causes is regarded as a true positive alert. So let's see the first research question. We explore the effectiveness of large language models detection. We could see that large language models could achieve at most 90% recall for this task, and the detection results vary significantly depending on the detection settings. And from here, we could see that the original detection precision could be quite low, and even for advanced ARMs like GPT-4, the recall could be less than 0.5. The precision issue is more pronounced for unconstrained settings. So when ARMs target small categories of misuse, simply relying on the model knowledge could be wrong. And for instance, it may require a padding algorithm for strip cipher, which is totally wrong. And conversely, the task-aware setting could enable ARMs to generate more true positive alerts. This result indicates that from the model performance perspective, it's better to define a focused detection scope. And we then investigate the false positive alerts. And we find that one major source of this is that ARMs can be misled by unrealistic cryptographic context, often found in the manually crafted benchmarks. And here is a test case which is designed to evaluate whether the model could detect an outdated digits algorithm, MD4. So for some models directly report that MD4 is an outdated algorithm, and this matches the ground truth. And however, advanced models may notice more context, like method names, and then extend their analysis. And in this case, GPT-4 noticed the method was named encrypt and mistakenly recommend adding a salt for it. However, as this case does not have a complete logic, we know that this is a handcrafted test case. So this report is unnecessary. We could see that while advanced ARMs try to reason over the broader code context, the benchmark often ignores the full structures and intent of the surrounding code, and this leads to the unexpected report. This issue is not real. We find that over 60% of the test case we examined in the past works could contain flawed or unrealistic code context. And such samples could include direct misuse introduced by the benchmark developers. Then this shows that even the professional developers could also make mistakes. And we also find some impractical operations that should not happen in real-world development. And in many cases, the code is functional valid, but it operates at a lower security level and should be enhanced. And this result shows that the flaws of existing benchmarks, when they suit pattern-based detectors, they might not fully capture the capabilities of ARMs due to their context insensitivity. And due to these influences, the original report of ARMs involves two main categories of errors. And the first category is from the misinterpretation of code semantics. ARMs may either misunderstand the intent of the code or the role of some local variables. And in these examples, ARMs treat a cipher name as a password, and then it reports a false positive alert. The second type stems from incorrect knowledge of the cryptographic APIs, where LLMs could mistakenly flag a circular API as vulnerable, and this leads to the false positive. And fortunately, the validation strategy could effectively correct false alerts. So for the real-world targets, LLMs could generate more precise results, but as the target size increases, LLMs could be misused when the size reaches the context window of such large language models. And we could see that the recall drops sharply when the file size increases. And there are also some special cases when LLMs actively ignore some misuse. For example, in this case, the LLMs notice the ground truth misuse as acceptable because the annotation referred to a corporate coding practice from another project. Then it tolerates some use of outdated algorithm. So understanding large language models detecting effectiveness, we then compare them with SOTA static detectors. And we could see that open source LLMs could already perform competitively to the SOTA detectors on our benchmarks. And for the ground truth misuse in real-world benchmarks, LLMs identify 17 unique cases where the previous traditional detectors could not find. And GPT-4 identifies 5 previously unknown misuse beyond the ground truth. And LLMs could also miss some multi-hop call chains, which involves multiple functions in a long call chain. We summarize large language models' advanced capabilities to uncover these known misuse cases. First, LLMs could extend high-level descriptions into a variety of scenarios. And this broader and more flexible rule sets surpass pattern-based detectors. And this capability contributes to identifying of 12 additional misuse cases. And LLM also performs some capabilities to do generic value resolutions, and it helps to identify the outcome of some logic conditions, and something like string manipulations result. And by focus on the detection of security-related context, LLMs are able to eliminate all false positive alerts in security-insensitive contexts. And despite of the advantages, we also identify some recurrent failing patterns, illustrate current LLM's blind spots. And remarkably, in 41.3% of cases, the error was due to the incorrect cryptographic knowledge. Interestingly, we find that LLMs from different vendors may generate the common types of cryptographic knowledge misunderstanding. And this suggesting a fundamental flaw maybe in the current training set of the large language models. And in over 50% of the cases, the false analysis was caused by large language models' misunderstanding of code semantics. We also classify these cases into 5 distinct categories, and please refer to our paper for more details. And for large inputs, open source models could generate totally nonsensical response, and this contributed to a small portion of the hallucinations result. And finally, we conducted a multilingual study across top Java and Python repositories on GitHub. We used optimized settings according to previous findings and interact with the maintainers of these repositories, maintainers for confirmation. We could see that the acceptance rates of LLMs reported misuse are much higher than traditional detectors. And we also find some interesting results in some case study. And we concluded the reasons why the developer of the popular repository maintainers misuse the cryptographic APIs. And one reason is standard involving. In a widely started project, the maintainer updates the TLS protocol in 2019, and 2 years later, TLS v1 was also deprecated. And this rendering the update insufficient, and the maintainers ignored it. And the second reason is most of the developers may mimic the upstream project. We found a special case when we interact with the developer. They said that they thought it was a valid operation since the OpenSSH also used it. However, we find that it is weird that NIST forbade it, but OpenSS still used the old algorithms and didn't update along with it. And most of the developers could consider the compatibility issues when they update an outdated algorithm, and the downstream developers could be affected by it. And one Apache project's maintainer told us that they attempt to optimize the logic according to our suggestions, but then they temporarily reverted the changes due to the user compatibility requirements. And for more discussion, please check our paper. So that's all. For conclusion, we find that large language models could complement traditional cryptographic detectors in detecting misuse in customized functions and the context-related security or insecurity operations. And the recurring failure patterns show that ARM's weakness and emphasize the necessity of reliable validation techniques and cooperations with static detectors. And for future works, we may keep going on eliminating the unrealistic code context from existing benchmarks and refine ARM's training data to reduce false cryptical knowledge. Yeah, that's all. Thank you.
Okay, thank you, Yifan. There are many useful and new discoveries in this report. Thank you for your attending this session. Thank you for the presenters and volunteers. We now have a break about 40 minutes. See you later.
So good afternoon, everyone. So welcome to the session of language model for program analysis and verification. And I'm Zhuo Zhang from Columbia University. So let's first welcome our first presenter, Guannan Wei, to present his work on hallucination-free, language model-driven sound and tunable static analysis.
All right, so my name is Guanan, and I'm going to talk about hallucination-resilient LM-driven sound and tunable static analysis. And this is joint work with Zhuo Zhang and Katerina Urban. So what is static analysis, right? The basic job of static analysis is to predict the behavior of a program without actually running it. And now suppose the problem. Now, suppose we have a program, and here are some concrete traces of the execution of this program. And the job of static analysis is to come up with an over-approximation that covers all of those concrete execution. Okay. Should I continue, or you can fix it? Or is that because the connector? Better? Okay. So we have this over approximation about all of those program behavior, and this is an important notion of soundness. So we don't really miss any true behavior of the program, and this is useful, for example, for verification, because once we have this over approximation, and if it doesn't reach an error, then we can safely conclude that there's no problem, there's no error in the program. And if there's indeed some error and it's covered by this over-approximation, we can say we find a bug in this program, right? So it's useful for bug detecting as well. But also, it's not always possible we can have a perfect over-approximation. Sometimes we just end up with a very coarse-grained over-approximation, and that covers some possible error. We report it in the static analysis, but they're not really something going to happen in the actual execution. So this is known as false positives or false alarms, right? So the goal of static analysis is twofold. One is we want soundness. We want to cover or detect all true errors. We also want to have precision, which means we want to reduce the number of false errors as much as possible. Now, you want to use LMs to do this kind of static analysis. The problem is how to do that. A popular way is to just really doing prompting of the language model, right? Here we have a Java program, and it's just doing some numeric operations here. And we can do have a prompt. The prompt is asking the language model to mimic the execution and detect the division by zero errors. And the language model indeed does a good job. It generates traces describing the execution and report some errors, okay? That seems all good, but the problem is, can we really trust those LM reported static analysis results? And unfortunately, because of those language models, they can hallucinate. We may end up with the result from the analysis. It misses a true error, which means there are real bugs missed by the language model, but also introduce false positives. So this is really bad. And you may thought we can validate the result from the language model, right? We can use even another language model to judge or validate the analysis result from the first language model. That seems possible, but to really doing this correctly, this becomes another static analysis problem, because without really knowing what's all the true behaviors, the other language model really cannot do anything to faithfully or correctly validate the result. Okay, so this is a problem we want to solve here. And our idea is to use language models as a meta-analysis. So instead of using language models to analyze a program and produce the behavior of the concrete execution, we use language model to analyze the static analyzer and also analyze the current ongoing static analysis. And the hypothesis here is, if language model can truly understand programs, and the static analyzer itself is also a program, so the language model can also understand the static analysis as well. Right. So here's a general recipe here. The first step is to identify those precision critical decisions in the static analysis. And those decisions, they should not hinder soundness, but also they have a huge impact on the precision. And the second step is, during the analysis, we use language model as that decision maker. And when we're prompting the language model, we should describe the process and the implementation of the static analysis. And the prompt should also contain the current abstract state, which contains, for example, the abstract environment, abstract heap, and also those other meta information of the analysis. And finally, the prompt should also instruct the language model to decide for better precision. Okay. This is a general recipe, and with this architecture, we can preserve soundness by construction, because those decisions, they have their own decision space, and neither or any decision is indeed sound. And if we're lucky enough, we have effective prompting, then we can improve the precision under this architecture. Right. So in this precision paper, we did a case study about the control flow analysis, especially for higher order programs. And this analysis task is to determine the functions to be called at each call site. And in general, this is an undecidable problem once the data and control flow are entangled. For example, when you have first-class functions in Scheme or other function languages, or even when you have dynamic dispatch in Java, or when you have indirect call with pointers in C. So you face the same problem of this undecidable control flow analysis. And our specific analysis we're working with is this abstracting abstract machine framework, which is a paper published many years ago at ICFP 2010. And in this framework, analysis is defined as an abstraction of a concrete abstract machine, for example, a CEK machine. And here I show the definition of the abstract state, which contains the expression, environment, the abstract heap, and also the continuation. And the result of this analysis is an over-approximated transition graph of abstract states. So following our recipe, the first step is to identify precision critical tasks in the static analysis. And in this AAM framework, there are several decisions, especially for abstract address allocation, exactly falls into this category. So in our case, we use LMs as this abstract address allocators. And here there are alloc v function and alloc k function. They are used to producing the abstract address for binding values and also for continuations. And those allocation functions, they satisfy those two important criteria. First, they are soundness safe, meaning that any allocation strategy from a finite set is guaranteed to be sound. And there's indeed a theorem showing that. And second, those decisions, they are precision critical, meaning that those addresses produced from those functions, they decide the degree of over-approximation. For example, context sensitivity can be captured under this framework. And the second step is to, during the analysis, we use the language model as a decision maker. And here on the right, I basically showed ARM prompting. I'm not expecting you can see the details here, but I'm showing highlight some of this here. At the beginning, we describe the data structure used in the analyzer. Like here, we describe the structure of the abstract state, okay, which have those different kind of states definition containing the program expression, the environment, the binding store, continuation store, as well as the current continuation. And we also describe the protocol of to interact with the language model. Like here, we specify the JSON format when we're querying a decision from the language model. And also, correspondingly, we specify the output format as well as in JSON format. And so the language model should produce exactly this JSON format. And then our analyzer will parse this result and put those things back into our analyzer used as the abstract address. And we also need to explain the logic behind the allocation and ask the language model to reason with abstract states. And this is basically to say we need to improve precisions in those prompts. So we have implemented this idea in a prototype analyzer. We use Scala to implement those analyzer, and we call language models. There's a Langchain4j framework to invoke the language model. We do have the open source here. We have done some very preliminary evaluation on micro benchmarks using GPT-4o. And here I show the result of the evaluation. There are only several micro benchmarks, and we also compare with existing deterministic allocation strategies showing in the top of the table. And because of language models, they are non-deterministic, so we run 3 times of our own analyzer and report those numbers. And here, for those 4 benchmarks, we show the number of nodes or abstract states and also the number of edges, and use that as an approximation about precision. And you can see here 3 of those benchmarks, we achieve the best precision compared to those deterministic existing strategy. And one of them on this MJ09, we have a pretty decent result. It's pretty close to the best one that is highlighted in the red box here. But overall, the result is encouraging, and we haven't really, we're still working on extending this into a larger benchmark. So to conclude, our position is to use language model to analyze the analysis, and we have a recipe for sound, precise, and tunable static analysis driven by language models. And the first step is to identify those precision critical decisions in static analysis, and the second step is to using language model for that. And in the paper, we also discuss other future opportunities, because other than the control flow analysis we have done in the paper, there are other kinds of analysis you can also discover this opportunity to apply. For example, for numeric analysis or termination analysis. And for the second recipe, the second step in our recipe is really about how we can use language models better. And there are also opportunities to do that. We can try different prompt optimizations, fine-tuning, or even reinforcement learning of the language model for better precision. This is the end of my talk. Thank you. From what we observed, it's pretty consistent. We try 3 times for each of the benchmarks. Be consistent, but there are definitely some randomness there. Yeah.
So I noticed you measured the precision, but you didn't say anything about the performance of the approach, because the allocation function is called quite a lot in these kind of analysis. What's the result there?
So currently our prototype calls LLMs every time when we need to allocate an address. This is indeed very costly. So some optimization, maybe we just do this selectively, or we can just customize the prompt or just selectively choose some of the prompt instead of giving all the, or reifying all those abstract states. But that's kind of like optimization there. Yeah.
And let's wait for a few seconds for restarting the systems. Everything work? Sure. So let's welcome our second speaker, talking about the work towards a repo-level program verification with language models.
I will start then. Hello everyone. It's with great pleasure to have the opportunity to present our work at LMPL today. I'm Steven. I'm a master's student from the University of Toronto, and today we will be presenting our work on repository level program verification using language models, where we try to extend some recent AI techniques into making verified software at larger scales. So in today's talk, I will first do a quick recap on what is formal verification. Then I will show how we extend and evaluate language model methods on large-scale software repositories using a new benchmark and a new context management framework. So a quick recap on why do we need formal verification. In usual software development, we try to make reliable software through test cases. However, those only capture the presence of bugs, but not the lack of any bugs. Where in formal verification, we parse the program behavior into a mathematical model where we then do reasoning and proves properties such as safety and liveness that are hard for test cases to catch. And some real-world examples that require high assurance is like flight control systems or OS kernels. To achieve verification, there is the cost of completing not only the implementation, but you also need to write the formal specification and completing the proof process that connects everything together. In modern verification tools like Daphne and Varus, they allow programmers to write these spec and the proof code in line with the executable code. So on the right-hand side, it's an example of a verified Varus program. Varus is a verification extension based on the Rust programming language. So we can see in yellow and in orange, we are writing spec and proof in concatenation with the implementation itself. These kind of verification-aware languages not only give a more readable and intact format for developers to work with, they actually also already automate a lot of the underlying logical reasoning. So given a simple problem with simple spec and executable, the various tool actually can automatically generate the verification condition, passing it into the SMT solver and letting the solver give a satisfiable proof. However, in many cases, programs aren't simple. And when we just pass the simple translation between executable and the specification into the solver, they cannot give a deterministic solution. And that is when we need to provide manual proofs aiding the process. Where with the additional proof, we will have additional condition that helps with satisfiability. So even though the tools already streamline the process a lot, it's not fully automated. Specifically from what we observed in real-world repositories, it's very common to see only 20% of the code lines being implementations, where the rest 80% are purely for verification purposes. And specifically with the huge amount of proof completion required, this is actually non-trivial. It's fairly difficult and requires expertise to come up with good looping variants, verifying properties about the programs, which can take even experienced users a long time to complete. And with that, this work, we specifically study the proof completion problem on a repository level setting, where we believe these larger repositories reflect a more practical situation of how software development is completed, where not only the volume is huge, but things are modularized into different files and components. And we assume and operate on a partially verified repository where many of the other functions are verified, but we are left with a few of the unverified functions missing the proofs. We are given their spec and executable, but we still need to verify the software and the function itself. So the repository setting does add additional complexity, first and foremost because of its huge context. There's thousands of functions and type definitions we need to work with and reason about. There's also the problem of cross-module definitions, where a helper function needed for this proof may be residing in a different file that is not currently accessible or not apparent. And within the repository level, because of so many lines of specification and proofs, it's really hard for anyone to follow on the strict syntax, streamlining the proof process. And in our work, we try to examine how we can utilize large language model capabilities to complete this proof process. And specifically, if we directly feed all of the problem and the entire repository into language model, it's fairly costly, and I don't think even today's model have the capability to ingest everything at a time. And because language models are actually fairly poorly trained on these verification domains, they also don't have a good knowledge about how to do these tasks. So it's very important to, in order to achieve higher accuracy, we need to provide a precise context and guidance to the language model. We address this by using the RAG-Various tool that we will be talking about, where it is a retrieval augmented method for context management. So specifically, we try to retrieve two types of contexts using the RAG-Various tool we are presenting to aid the language model. The first thing is what dependencies and premise does the current proof completion task require, where we try to identify previously defined help functions that is already existing in the repository that can be used in the proof process directly. Secondly is about pattern understanding. We need to teach the language model how to approach this particular task in terms of the proof pattern and practices. So we want to find how similar functions are proved and using that as a scaffolding for the proof of the current question. And next, I'm going to give an example on how we extract these two contexts using an example from a real-world repository containing unproved function. And in turn, we show how this retrieved context aid the proving of this particular unverified function. Here it's very small, but we look at a real-world example on a implementation of a locking mechanism, where we have a function called lock release that is unverified. It has the implementation code and the specification that can't be verified by the SMT tool automatically. From here, we try to find useful context about this function by looking at other similar functions within the repository. Specifically, we define similarity by two means. First of all, if there's other code that is similar to the task code in terms of the syntax or semantics. And secondly, if the other code has common static properties, like what kind of type definitions are used. In this case, there's in the parameter list, there's a lot of tracked variables, so maybe that's a hint of what we want to look for. And also, if these files reside in similar file organizations. And luckily, in this case, we are able to find another example function that is already verified. So this is the lock acquire. We can notice that within the acquire function's proof, it uses some dependencies, such as this one called tracked insert, that is a helper function it uses. And secondly, we also notice it uses some practice of having actually a ghost helper helper variable declared before doing the proof assertion command. So we actually extract these two contexts as helping informations for the language model and pass that synthesized context back to the language model in order to prove our original question about how do we prove the release function. So in this case, we are able to successfully use the retrieval method to gain a much better context about what we are doing and how to do it. So in order to achieve such context retrieval, we need to prepare the corresponding search indices in order for efficient retrieval at runtime. We do it on a per function we do the indexing on a per function basis. For the first index, we turn the function code directly into high-dimensional embeddings and store that for similarity search in the future. Secondly, we extract the metadata about each functions, things like we've mentioned, what kind of type declarations are used in the function, any class inheritance associated with the particular functions. Many of those come from similar terminologies in context organization from program generation in general. So we then summarize this metadata and index this into a separate index as well for a quick lookup at runtime. This is a sample of what metadata may look like. And these items set up our main pipeline for the reg various. So when given a repository, we want to first create the corresponding indices by parsing the context. And then when given a particular proof completion task, we are able to retrieve the useful context through either code or the metadata and help language models reasoning with the pattern scaffolding or the helper function extraction process. Lastly, we pass the synthesized retrieval results to language model for final generation, and this is a visual flow of the process. So in the indexing and the retrieval we've talked about, after that is the proof generation process, where we either choose to do a direct generation based on the context and problem we give to the language model, or in additionally, we can do a refinement process where we take the feedback from an error message from the verifier or compiler and let the language model try to auto-correct itself again on how to repair the proofs. So with that, we want to put this into evaluation. We introduce a new benchmark called repository verification benchmark, RV-bench. It is the first kind of benchmark in this kind of verification aware language dealing with repository contexts. And it is sourced from 4 complex and real-world various projects offering a diverse verification testbed, ranging from things like verified Kubernetes controllers to verified distributed key-value stores. Here's an overview of the specifications. But in general, we are able to provide 750 more proof tasks covering more than 12,000 of proof lines. And among the verification tasks, to the maximum, the verification problems aren't trivial. To the maximum, we can have some functions requiring more than 80 lines of proofs in order to prove a single function. Lastly, the logic breadth required to do this proof completion on this benchmark. These task problems in RV-bench capture some kind of logic ranging from linear logic to separation logic, which deals with memory safety guarantees or concurrency guarantees and more, which is more complex than what previous benchmarks provide. So lastly, to evaluate whether a completed proof for a function is actually correct, we need to evaluate the success, and it's measured by being verified and intact at the same time. Verified meaning the completed function compiles by the various compiler and passes its verification process. And intact meaning the original spec and executable aren't altered. Here we'll just provide a very quick highlight summarizing the key evaluation results. The baseline we compare to is AutoVarious. It's another proof completion tool for Various, but does not have the smart context retrieval capability. And for our side, we provide 2 invariants concatenating our context retrieval method with either direct generation or refinement. And we can see in all cases, with the smart context retrieval, it's able to perform a lot better. And we believe that specific and task-guided contexts are promising in reaching better software verification. I will leave anything else for questions, but that's the main thing I want to cover on the core of our project. Thank you for listening, and I will welcome any questions.
So you mentioned that part of this was ensuring that the specifications were unchanged and the implementations were unchanged.
Yes.
Yes, but I think in practice, it's sometimes necessary to strengthen a specification in order for a proof to go through, or perhaps change even the implementation, not the ultimate result, but change the implementation to perhaps use less strange language features to simplify the proof.
I see, yes, definitely. In real practice, it's fairly more practical to have the iteration loop between implementation spec and the proof, right? In our setting, it is a more of a simplified situation where we assume we have a good idea about what the program does. So there is a specification given, and there is somebody already gave implementation. So we are just doing the proof completion, verifying whether they match.
I see. I was just curious though, if you were thinking to like extend to a context where maybe the specifications themselves don't fully specify the behavior, how would it be possible to extend this approach to that, you think? Or
yes, specification, especially auto-formalizing specification from other sources is a difficult problem, and it's not a particular target of this task. I know there are many other exciting work. There's recent Verena or some other verify benchmark that deals with this end-to-end thing.
Cool, thank you.
Hopefully it answers some of your question.
And does one task contains more than one function?
Currently, we only complete one function at a time. Right. So our statistic doesn't show a union over multiple completed functions.
Right, thanks.
So you showed in the benchmark set how many lines of proof code were needed to verify the property, I believe. But that's in the original benchmark, right? Or wait, you didn't show this on the presentation. So I was actually wondering how readable the resulting proof is compared to human written proofs.
I do have another slide showing a blue score comparison, which compares the text similarity between generated proof and the human written proof. With the RAG-based methods, it does show an increase in the blue score, so the generated answer actually more closer to what the human write because of this in-context example, but not particularly on manual inspection between exactly how readable they are.
To exchange the screen. Okay. Thanks for the introduction. Hi, I'm Zhongyi, and I'll present the precast. It analyzes, it specifies, and it verifies. This is the joint work with Teng Jie, Ming Shuai, and our other collaborators. It is often said that program synthesis is the holy grail of computer science. In this talk, we explore what is the holy grail of formal verification. Typically, formal verification acts like a complex machine. It takes programs and specifications as input and output a simple yes or no. To achieve this, many specific methods have been developed. In this landscape, verification power generally increases from bottom to top, while the level of automation decreases from left to right. Our work focuses on two key methods: sound static analysis and automatic theorem proving. We ask, how can we improve their automation and scalability? Okay, I'll change it. Here, I will introduce a synergistic framework that combines the strengths of both, achieving powerful automation and scalability. Let's see how our framework works. We start with static analysis. Consider a program with a function that returns the absolute value of x. Suppose we want to check for runtime errors. A sound static analyzer such as pharmacy RTE can generate an assertion before line 1. This assertion states that if the predicate phi1 is violated here, for example, x equals to int min, then an integer overflow will occur. However, due to the abstraction, the alarm can be a false positive. An analyst would then need to check all execution traces reaching this assertion is valid or unsatisfied. In this case, it's easy to see that the call at line 2 is safe, while the call at line 3 triggers a real overflow. But what about the real-world large-scale programs? Consider this nuclear power plant software with 17,000 lines of code. SOTA analyzers generate hundreds of alarms. Manually inspecting each one to determine if it's false positive or a real error is not only tedious, but also highly prone to human error. This is where a practical verification paradigm comes in. We use a sound verifier to discharge the false alarms and help identify the genuine errors. To use the verifiers such as pharmacy WP, we must first provide specifications. Here, we write a precondition phi2 for the apps function, which requires the input x must be larger than int min. By assuming this precondition holds, the assertion phi1 is verified to be valid. We mark a specification as green if it is verified, otherwise it is red. Then at each of the call sites, like line 2 and line 3, the verifier checks whether the precondition phi2 is satisfied. In instance, these preconditions act as guard assertions at every point where the function is called. For the call site at line 2, since 42 is larger than int min, so the precondition phi2 is satisfied. But for the call site at line 3, the precondition phi2 is violated since the input equals to int min. So an alarm is reported here, and a verification expert have to identify whether it is a false alarm or a real error. Now we have present the workflow of this synergistic verification framework, which combines static analysis and deductive verification. The core problem is, for RTE freeness verification of real-world large-scale programs, the specifying stage still relies heavily on human expertise. To mitigate this problem, there are a lot of recent studies focusing on utilizing LLMs for automated specification synthesis. The common idea is a guess and check iteration framework. First, in the guessing phase, an LLM is prompted to generate candidate specifications for a given program. Then in the checking phase, a verifier validates these candidates. If verification fails, the invalid result is fed back to the LLM to generate new candidates. This loop continues until a valid specification is found or a resource limit is reached. However, this method exhibits scalability limitations when applying to large-scale programs, primarily due to two bottlenecks. First, these methods often feed LLMs with the entire program as context, which may exceed the model's context window limit. Second, and more subtly, these methods struggle to synthesize fine-grained interprocedural specifications, which are essential for scaling verification, but are harder to generate. Let me clarify this point. First, what are interprocedural specifications? Consider the program with its core graph. The function main calls the functions 1 and 0, and both of them call the function ID, which simply returns its input x. At line 1, the return value of ID1 is used as a divisor. A static analyzer may raise a false alarm 5-4 here, warning that the divisor could be 0, which is obviously impossible. An ideal way to discharge this false alarm is writing a post condition 5.5 for function ID, which states the return value of ID equals to its input. With this post condition, a verifier can prove the divisor x is actually 1, thereby proving the RT assertion 5.4 is valid. So here is the key insight. For programs with complex core hierarchies, verifying properties such as 5.4 in function 1 requires specifications in different functions, such as 5.5 in function ID. These are so-called interprocedural specifications. Generating such interprocedural specifications is hard for existing LLM-based methods. Some are limited to intra-procedural specifications of certain categories, such as loop invariants and assertions in individual functions. While other methods can generate interprocedural specifications, but they treat them as a holistic block without modeling their inherent differences, which leads to problems. As subfigure D shows, if an LLM sees the alarm in function 1, it might be misled and generate a precondition 5.6, stating its input cannot be 0. This is a typical over-constrained precondition, since function ID can accept any integer. Remember that the preconditions act as guard assertions and checked at all core sites. This over-constrained precondition induces a new false alarm in function 0 at line 2. Because 0 is passed as input into function ID and thus violates 5.6. This demonstrates how LLM hallucinations can introduce over-constrained preconditions and induce new false alarms. So when we back to our synergistic framework, as we just discussed, the bottlenecks of existing approaches can be concluded into two primary challenges. The first is the context length limitation, and the second is the lack of a fine-grained strategy for generating interprocedural specifications. To resolve these challenges, we propose PreGAS. It is built on the analyzing, the specifying, and the verifying framework. Our core contribution lies in automating the specification synthesis phase. The core idea of PreGAS is simple: divide and conquer. Our framework had two key stages. I will not introduce the details. Stage 1 tackles the LLM context limit. Instead of processing the whole program at once, PreGAS decomposes verification into smaller and manageable tasks called VUnits. Each VUnit contains just the guard assertion and the necessary program context. So the VUnit is perfectly sized for an LLM. And stage 2 addresses the need for fine-grained specification synthesis. Its main idea is to generate specs tailored to their context. Specifically, for a given V unit, it generates preconditions and the loop invariants for the host function where the guard assertion lies in, such as this function. And for their COE functions, pregas generates post conditions and the loop invariants. And we evaluate pregas on a module of real-world X509 parser with over 1,000 lines of code and 20 functions. To verify it is free of RT, the developers construct 251 specifications. And pregas automatically generates 108 specs and verifies most assertions. Ultimately, a human expert only needs to modify 39 specs based on pregas outputs to complete the full verification. This means pregas reduced the human effort by 84.5%, demonstrating high automation and scalability. Besides, the entire process takes less than 3 hours and under $4. This is a marginal cost compared to the days of effort that a verification expert would typically spend on such module, highlighting the great efficiency of our framework. Here is the conclusion. We propose the pregas framework and foresee that by adopting such two-stage divide and conquer strategy, we can pave a compelling path toward the automated verification of large-scale programs. Thanks for your attention.
So thank you for your talk. And I'd like to ask if the specification generated by the large language model cannot be verified, do you make some feedback to the large language model to let it modify its specification, and what form is the feedback?
Yeah, there are many details during the stage 2, because if a candidate fails, then the verifier will return its feedback, such as proof obligation and the verification condition. Then you can use this information to ask LM to write stronger specs.
Yes.
And you can use a chain of thought. Actually, I may prepare some slides of this work. Okay, sorry. I didn't prepare.
Okay.
Do you have any questions?
Oh.
Sorry.
Oh, I see. Thank you. Okay.
Hi.
Hi.
Very quick question. So in your evaluation, did you end up manually checking the specifications to see if they are good quality or something?
Yeah, very good question. And actually, we do. You see, like this X50 parser, the developer write 200 specs to guarantee it's free of RTs. And pregas generate 100 specs. And we, based on these 100 specs, we found that only we need to modify 39. And you can see the combination is much less, because we found a lot of redundant specifications in the in this project, because some specs are assertions that describe the program states of some locations. It is not useful for the RT assertion, for the verification.
Okay, thank you.
Okay. Okay, thank you.
Hello everyone. I'm an undergraduate at the University of Toronto, and today I'm going to present our evaluation and a case study on two rock projects. So first of all, what is software verification? I mean, we're here at ICFP, probably all of us are familiar with it, but I still wanted to include some primer on how software verification goes. So software verification can prove the absence of bugs. Successful examples include CompCert, SCL4 microkernel, and many more. And how does it work? Well, you take a specification, such as this function should always return a sorted list. You take a program, and then you write a proof using either proof assistants, such as ROC, Lean, Agda, or you help guide a proof assistant using automated Turing provers, and sometimes called autoactive Turing provers, such as Daphne, Varus, Y-Tree, and many more. And then if the proof assistant does not give you any errors, then you say that your program obeys your specification. So your program should at least be correct. And as an example, this is the ROC proof assistant, which we evaluated our case study on. So this is a definition of a stack. You can push, you can pop. The exact syntax does not matter right now, but what matters is the fact that ROC has a small trusted computing base where you can write proofs, and if your proof passes the check, then it means it's 100% correct. And this is an example theorem where if you push something and then pop it, you get the exact same results back again from the stack. And you can see that QED is right now underlined because we haven't written a proof. And then at the right-hand side of your IDE or text editor, you can see this proof goal. And then as you write some tactics, which is basically writing your proof, you will see that QED line will disappear if you successfully complete the proof. Okay, so what's the problem with software verification? Well, verification is costly, and most of the programmers like to code, but they don't like to test or prove. I mean, can you blame them? Sometimes this is an example proof from Verdi. Yeah, you can imagine how long these code bases can get. The question is, can the LLMs usually automate proof writing? And particularly, if they can, what kind of context do they need about the code base? And because we have a context limit in the LLMs, we can't just copy and paste the entire code base into it because the LLM will forget and this performance will reduce and so on. And yeah, of course, another bottleneck is the price. Even if you could, hypothetically speaking, put your entire code base onto the LLM. And how can you make your code base LLM friendly if you just want to prove it? And do you want smaller proofs? Do you want everything in the same file? Do you want things in different files? How do you want it to go? And how does your code base affect the LLM's proof writing performance? And most importantly, how are the qualities of proofs generated by LLMs? So, I mean, they can pass the proof checks in ROC, but how are they? Like, are they smarter, like more elegant than maybe human proofs? Well, we are going to attempt answering all of the questions. So for our study, we picked two ROC projects. The first one is Verdi, a framework for implementing and verifying distributed systems. It has around 579 proofs. And just to give you an idea of the size, 19% of the proofs have 25 plus tactics, and majority of the proofs in Verdi has around 5 to 9 tactics. I will introduce the exact numbers later. And for another project that we picked was HS2Coq, the base library of HS2Coq. It translates a subset of Haskell to ROC so that you can reason about your Haskell programs. It has 187 proofs, and 5% of the proofs in there has 20 plus tactics, and majority has around 0 to 4 tactics. And just as a note, both have relatively old ROC versions, 8.11 and 8.10.2 respectively. So how do we answer our questions? Well, first of all, we have this notion of dependencies, and we extract the dependency for each proof. So a dependency is any signature that the original proof relies on, including definitions and theorems from any other source file, including lemmas, notations, records, definitions, and so on. Another, in the stack example, this is push, pop, and the stack definition itself. Another concept we have is the lines before that come in the file. So for a file, all lines that come before where the given proof begins are also given to the LLM in this ablation. So this works because ROC doesn't really scan ahead, so you can't really hoist the proof, and you have to refer to definitions you have written before and terms you have written before. And we define success as if you can write QED at the end of the file without using any assumptions or cheats, basically like admitted. Okay. So we also have 4 different evaluations. So we have full context informed. So this mode includes both external, which is other file dependencies, and all of the previous lines in the file of the proof. Another evaluation we have is no external dependencies or notations, but this one includes all of the lines that come before in the file. The third evaluation is without in-file context, which still includes the same file dependencies. So even if you have different dependencies in your current file, we include them as long as they're in the same file, even though we're in the in-file context. And for the fourth one, we have no context provided at all. So we just give the LLM the proof and the signature, and we ask the LLM to complete the proof. And we evaluate on GPT-4o Mini, GPT-4o, O4 Mini, DeepSeek Prover V2, DeepSeek R1, and O4 Mini and DeepSeek R1 are reasoning models for context. And DeepSeek Prover V2 is trained with lean proofs, just in case you don't know. And DeepSeek Prover, well, we're including DeepSeek Prover V2 because we're interested in whether it has learned from writing lean proofs or being trained on lean proofs, and whether it can also work on ROC as well. So what are all of the results like? Well, these are the results in short. I mean, I'm not going to just let you look at those. I have a few takeaways, but overall, you can see that for HS2COG, which has around 187 theorems, we can get around up to 51 to 52% accuracy with the best model, whereas with Verdi, you can get around 30% accuracy with the best models. Okay, so what are the takeaways you can have from this table and moreover from our study? And just an important note for this table is that this does not involve any feedback loop, so we just gave all of the proofs once, and we did not give the LLMs any feedback at all. So this is just calling the LLM once. Okay, so what are the takeaways? Well, models perform the best with more examples in terms of ROC syntax. We all know models perform best with examples usually, but one interesting thing is that models don't really properly know ROC syntax, first of all, because there are usually many syntax errors that we have figured out in our examples, in our evaluation, and many syntax errors that were caused by the compilation process. And when we give the lines before, even if the lines that come before in the file are not necessarily related, the model seems to at least learn the syntax a little bit, which is surprising considering large language models should know the syntax, at least get it right. Another takeaway is that context retrieval is crucial for automated proving, and the largest drops in success rate occur when the information is omitted. And this is another point where you have to be careful about what you provide to the LLM because of the price. So here we have included a token count for each ablation. For example, if you just include everything in the code base, then it can go up to 3,300 tokens for one proof. Or in Verdi, it can go up to 7,000. So it is going to get really expensive very quickly. And another question we had was, do LLMs really copy the answers? As in, do they really generate the exact same proof that was present in the repository, including we just do an equality check, string equals equals. So here in this graph, you can see the exact same figures, exact same proofs highlighted in dark, and then the original success rates in lighter colors. And in the x-axis, you can see the interval ranges. So for 0 to 4 proofs, you can see that the LLMs have kind of copied the proof, but it doesn't really mean anything as much in this case, because 0 to 4 tactics, you can pretty much have an identical proof by coincidence. And this is for HS2COG. And another takeaway here is that LLMs perform better on small proof sizes, but I would just want to show you Verdi right now, which you can see that still for lower number of tactics, the LLMs have kind of generated the exact same proof, which is expected, but it has also generated exact same proofs in longer tactics like 20 to 24, or or proofs involving 15 to 19 tactics. Yeah. Another takeaway is that the impact of adding or omitting information depends on your project structure. So, for example, one really interesting thing is for HS2COG, if you add more context, it actually decreases the success rate. And for example, this graph shows how much percentage you lose from going from just dependencies only to including the previous lines in the file, which are not always necessarily related. So in this case, you can see that for larger proofs like 15 to 19 or 20 plus, it just causes the model to get confused. So again, do not give the entire repository like you would with just copying and pasting to ChatGPT or something else. Okay, so another thing is we want to ask how is the quality of proofs generated by LLMs? Like, are they elegant, or are they like maybe shorter than human proofs? Okay, so in our first example, this is an example from HS2COG, and I mean I'm not. This is quite hard to read, so I'm just going to give a summary. Well, in this case, in this proof, what we're doing is we're doing a case analysis on the equals operator, which gives you two cases when the equals operator, let's say x1 equals to x2, is true, and the case when x1 is equal to x2 is false. And this is the original human proof that was found in HS2COG, and this is a proof generated by DeepSeek R1. And what is really surprising about this is not the fact that it's just shorter, but the fact that it has chosen to do the case analysis on propositional equality, so x1 equals to x2, rather than x1 equals x2. So it is taking a different approach, and again, the LLM doesn't really know the original proof. We did not give the proof to the LLM. It's just taking a different approach, and it's just making the proof kind of smarter in this case, and this was really surprising to us. Another really simple example is from HS2COG again. Here you can see that we're just introducing the variable, destructing variable, and then calling auto over and over. So you can the LLM just realizes this. Again, it does not have the proof, but it just figures it out on its own. It says, okay, I can just chain the tactics together using semicolons, and then I can just complete this proof really quick like this. And another thing, and another interesting example comes from Verdi, where the proof is quite long. There's like around 29 lines in this proof. But I mean, the proof, how long the proof is, does not really matter in this case. But what is important is the fact that Verdi developers, chose to copy paste, which is okay. But then the LLMs, in this case, O4 Mini, realized that this existing lemma is a contrapositive of another a theorem that already existed in the code base. So it was able to figure that out because we included all of the previous lines in this case. And it was able to figure that out, which, using contrapositive is quite good. And there are also cases where the LLMs are not necessarily doing well. We set the temperature to 0.1. So we hypothesize that this might have caused the LLM to just repeat a few things. Like, for example, it just gets stuck at rewriting equality operator, just goes on by repeating the rewrite. And yeah, so there are some cases where the LLMs still get stuck. And to conclude, LLMs can be good at proof generation, but you have to give them the right context, and context retrieval is important. LLMs can work better with small proofs, but they can also do larger proofs, but they still can output small things and still get the proof right. And the larger proofs the LLMs write can be shorter, but this is surprising because they're not shorter for one reason. They're shorter for various reasons. If you're interested in a more detailed explanation, you can also read the paper. And if you're interested in what future work you can do in this area, is that one really important thing here is that we need more software verification benchmarks, especially for ROC and its latest versions, because HS2Coq and Verdi are in versions 8.11 and 8.10. So an updated benchmark for ROC would be quite nice and helpful. And another point to note here is that existing benchmarks of interactive theorem provers mostly focus on math and Lean 4. But previous research actually shows us that software verification can be harder than just writing math proofs. Well, there are two different areas, but if you compare the success rates in latest benchmarks, you can actually see that they're actually quite low and sometimes even less than 10%. And in fact, in some cases, LLMs can also get 0% with some automatic verifiers like Verus, Daphne, Ytree, and so on. Yeah, and there's some recent work in this area includes Verina, Clever, Verified as Benja, and so on. And software verification benchmarks for LLMs, especially software verification benchmark for LLMs, especially ROC, are underexplored, as I've said. And some other questions: how do LLMs do with refinement in our code base? We were not able to, in our study, we were not able to actually run the experiment with refinement. But if you want to modify our code base, so if you want to, run the experiment in our code base, we actually support refinement in our code base. Just with a really simple change, we extract the error messages as well. And what are some good methods to retrieve context? Should you apply retrieval augmented generation? Should you maybe use another LLM to retrieve context? Or how would RockHammer context extraction do, or premise selection do in this case? And if you're interested, you can scan the QR code here to read our case study paper. And thank you for listening.
Hi. So if I understand this right, like you took, let's say, HS2Coq, you kept all the definitions, you kept all the properties, and then you removed all the proofs, and that's what you, but of course that means that you still, like, you know, if let's say I'm writing HS2Coq, there's a bunch of properties that I care about, and a lot more that I'm going to add because they're useful lemmas on the way to getting to the thing that I really care about, right? Like lots of invariants, whatever. So my question is, have you tried removing those as well? And because, you know, there's a lot of creative work is already being done just by coming up with the right invariants. Like that's also hard work, right? Like by the time you get, ideally by the time you get to the actual thing you want, that's very easy to prove because you've put in all the work of, So is that something that this can be?
You mean removing sorry, could you repeat like the removing part of the question?
Like imagine that you have one or two key properties. Those are the ones that you actually want to prove about your software, right?
Yeah.
But before that, you have a whole lot of lemmata, right? And a whole lot of invariants and whatever. And if you haven't come up with those yet, then it would be much harder to prove the thing that you eventually care about.
Yeah.
But if you keep all those, you're kind of guiding the LLM down the same path that the human has come up with.
Yeah, so well, in this case, because there are a lot of proofs, it is going to, well, we haven't explored that, but I mean, you could theoretically take them and take the few theorems that you mentioned, or lemmas, or properties, and then omit them and then rerun as well, but we have not done that. But I guess it would be a good idea to explore, because,
Okay, thanks.
Hi. Actually, our team did a similar job. So we are Copilot team. We're all here. We would be happy to chat. And I have a question regarding data contamination. You ran your benchmark, and how are you sure that LLMs haven't previously seen the proofs for your theorems?
Okay, thank you for the question. So, well, we can't truly be sure, but this is why we just wanted to check if these two things were equal. But this is not a perfect way to check it, and I don't think there's an easy way to know if it's included in the training data. But since these projects are on GitHub, I think it's safe to assume that they might have been contaminated or be seen by LLMs. But again, I don't think there's a good way to check for it. And another point to mention here is that Verdi is actually in another study called CogGym. So yeah, Verdi was in another benchmark as well. But I agree with you that there might not be, they might have been previously seen.
Okay.
The idea was that if we check maybe for equality to demonstrate it here, maybe we couldn't know, but yeah.
Thank you.
And I guess for the next talk, it will be the live remote, so there's no actual speaker here, so let's just wait for the monitoring. Yes. Hello, can you hear us? I guess you mute yourself. Sorry, we still cannot hear you. Is our side the issue or? Yeah, can you speak? Try again.
Yeah.
Yeah.
Yes, can you hear me? Okay.
Great, we can hear you.
Okay,
So,
phew.
yeah, so please start your presentation.
Okay, let me share my screen. Sorry, are you able to see the screen okay?